Okay, we're recording, and this is February 14th, 2022, and this is the Yaskawa Monday morning VFD training class. It also happens to be Valentine's Day, which means you better get your act together or you're going to be in trouble. To me, this is called Bear Trap Day, because if you do everything you're supposed to do, life's okay. You don't get any credit because you're supposed to do it. But boy, if you miss this holiday, it's like sitting in a bear trap. And it's going to be a year till you can redeem yourself. So don't forget, get those flowers out. Today, we are going to talk about some of the special software products that are available on Yaskawa drives. And as I said in the invitation, I think this is one of the things that makes Yaskawa really special. 20 years ago, our reliability, our ability to run things without blowing up was much more special than it is today, because a lot of other manufacturers, bless their hearts, have upped their game and they're coming closer to being reliable in most of the applications. On that point, I will say that I don't think I would put any other drive other than a Yaskawa on extruders, on heavy duty hoisting. We certainly have outperformed everybody in the agricultural pumping environment, which is a variable torque application, but it's really difficult because of the nature of the environment. So there are still areas where Yaskawa and their crazy quality is appropriate and almost exclusively required. But for the most part, we have 10 competitors out there that are making drives that are reliable. Perhaps I should do a session on why Yaskawa unit is more reliable than other units. It comes down to the small details these days, and I'll mention a couple things on it before we move on. The fact that we have digitally controlled power supplies that regulate their output, as opposed to diodes and transformers. The fact that we source all control power off the DC bus, which is behind the harbor wall, so to speak, from the incoming line. Little things like that are reasons why our drive doesn't fail. Conformal coding. We're not the only people that do conformal coding anymore, but we used to be. And that, again, helps. We also know how our drive performs all the way up to 160 degrees Fahrenheit. We have charts and data on that, and it allows us to pick applications that are, for the most part, beyond the 40 C standard, which is 104 degrees Fahrenheit, and perform well because we've engineered the drive and selected the drive properly. So these are all small things that make Yaskawa still the most reliable drive in the business. We have a remarkable amount of IP in terms of current sensing, not just for the very important task of operating our field-oriented control of motors, but for our fault trip before component failure philosophy. So that's certainly something that makes Yaskawa stand out even today, although somewhat less than it was 20 years ago. Special software, special application software is something that still today puts us head and shoulders above the rest of the pack. And we're going to talk about some specific products. I'm going to call them products today. To give you a couple of examples of how important these products are in how we service our customer base in certain applications. Ever since I've been in drives in California, and the reason I came to California was because we had an ability through special software, in those days it was on an EEPROM, to master and safely operate bridge cranes. Today, through one of our largest customers, which is a company called Magnatech Electromotive, we dominate the crane and hoist industry. I believe we have more than 3/4 share. The crane and hoist industry led us to develop special software back in the 90s for other applications. We happen to dominate the commercial laundry industry because we developed special software to allow the industry to use a single-speed motor instead of a two-speed motor and still operate during the high torque, low speed agitation cycles and spin up that single speed winding to the extraction cycle, which is where you centrifugally spin the water out of the load. And you're familiar with that on your own residential washing machines. We also came up with out of balance using the motor as sensor technology that we have been very good at. And because we could detect through our current sensing that the motor was producing out of cycle torque, we could then set a tolerance on that. And when we exceeded that tolerance, we would stop the load, hard reverse it, theoretically flipping the wet cloth in the drum of the washing machine, and then try to accelerate to extraction cycle once more, again, still detecting the torque and seeing if it was still out of balance. These type of things were done with a standard variable frequency drive. In the case of the laundry machine, it was done open loop without an encoder. We advanced this in the IQ Pump software. IQ Pump is a standard drive with special software specifically tailored for the agricultural pumping application. We absolutely dominate that market. And especially out here in the West, where water is so important, you can drive up the 5 and the 99 freeways, and you can see white IQ Pump enclosures standing out in the full sun, hooked directly to the pole transformer and operating reliably. Now, here, both of the things I've mentioned about our advantages as a drive manufacturer come into play. We have superior firmware that makes the drive very easy for the farmer to operate and takes into account, again, using motor as sensor technology, things like a period where the motor is running, but there's not enough flow over the submersible pump. And submersible pumps require flow to cool them. If the motor's running and generating heat, these are induction motors, therefore when they're running, they're at least pulling no load, and therefore they're generating watts losses. And if there's no flow, that motor will overheat and it will destroy itself downhole, and it'll cost you $10,000 to $20,000 to pull it out, not to mention the potential damage to the casing of the well. We have no flow protection in the firmware using motor as sensor technology. So the special firmware has advanced over a dozen years. And the main reason for our success in the agricultural firmware is that we listened to the customer and we revised the software numerous times to the point where we now have an outstanding product. Of course, the other thing I mentioned, the environmental ability of our product, properly engineered, is the other half of why we're so successful in that market. Today we're going to talk about some products that you might not be aware of that are available to you as typically a $500 list adder, although, and I will speak to this for a moment on the commercial sense, sorry, I'm hesitating here because the program's supposed to automatically admit people, and I'm not sure it is doing that, but I'll keep an eye on it. So the commercial side of this, is that we have a special software product. In some cases, it does require an additional piece of hardware, such as an encoder card, to allow us to close the loop to perform the function of the special software product. And if you look at the price books in the past, we have been charging for that. So I'm going to spool up a price book here and share the screen. The softwares were on average $300 to $500 list, and then you had to add the extra software in as well. So let me share the screen here. There we go. Okay, if you can't see the price book, somebody chime in and let me know that I'm screwing up. This is the A1000 price book. And if you go down to options, and page down to
Pierce, you could just hit plus a couple times.
Thank you. How's that?
Awesome.
Application-specific firmware. Here is the electronic line shaft. By the way, you will always get a dash 3-digit addition to your part number when you order a drive with special software that is installed at the factory. And this is the only way we used to do it. Here you have 064, which is the adder for the software itself, and 065, where you ask the factory to pre-install the 2 PGX3 cards that are required to operate this software. And this is the first software we're going to go over with when I get into the technical side of this class. Notice again, we're about $500 for the spindle orient software. There's a motion control software that's not in this price list. Output voltage PID is a very simple software that allows you to decouple the voltage from the frequency on the output. As you know, a normal variable frequency has a fixed volts-hertz ratio that it may vary a little bit to do some torque control, but output voltage PID allows you to PID on the voltage separately from the output frequency. And this is used when you want to use the drive for non-motor applications, such as a digital power supply. We've used this very successfully in regulated power supplies for medical equipment. Here is our high frequency software. I believe this software is ITAR controlled because it's 1,000 hertz. It goes above the 590 limit that we are allowed to sell to you open market. And this has to do with the Iranian situation of centrifugal or centrifuges for processing enriched uranium. But we have 1,000 hertz high frequency software. We also have an 1,800 hertz high frequency software. A lot of things that I'm mentioning here are not in the natural price book. So part of this class is to make sure that you understand that we have a lot of other products that we don't publish. Now, our new this is an A1000 price book, and most of these softwares have not been migrated to the GA800 yet and will be migrated to the GA800 once we get enough time to do so. Our QC process means that this is quite an endeavor. Electronic line shaft has passed muster and is available, although we haven't commercially spoken much about it, and it's not even in the documentation for the GA800 yet. But what we're going to do, actually what we already have done, is we're eliminating this charge. And we are allowing you to download the firmware from the Yaskawa website. This is the firmware download. You can flash this onto a GA800 drive using Drive Wizard. And then you need only to add the cost of the two PGX3 cards, which are, which is $330. So that's the commercial path that we're taking with our firmware products, special software products. You also will hear us refer to this as CASE, which was an acronym that we came up with early on, and it stands for Customer Application Software Environment. So let's talk about electronic line shaft. This is the electronic line shaft manual for the A1000. It's not going to change much when we publish it for the GA800. And I think this is actually one of the coolest softwares we make. So let's get through all the lawyerese and get to how it works. In this configuration, this is a master follower software. The firmware for electronic line shaft, it resides on the follower drive only. It does not have to reside, and usually doesn't reside on the master drive unless we want the ability to switch back and forth in terms of functionality, in which case we'd install a second PGX3 card on this drive. But this is the drive that is the electronic line shaft follower. What electronic line shaft essentially does is it allows you to take an external pulse stream, encoder input. Oh, people are waiting in the lobby. Son of a gun. And I'm not seeing it. Okay, sorry, Andy, for leaving you out in the lobby so long. For some reason this morning, the automatic entry isn't working. My apologies. We are into the technical side of the electronic line shaft software. The electronic line shaft software resides on the follower drive, and it allows you to basically sync this motor shaft to this pulse input from the master drive. Now I'm going to tell you that we don't need a master drive. All we need is an external encoder input. We'll follow any pulse train. We prefer it to be quadrature. Doesn't even have to match up in the parts in the pulse per rev to this encoder, which is the encoder input that we use to commutate the motor. Any pulse train, throw an encoder on a shaft, and we will lock this shaft to that shaft, not in velocity control, but in angular orientation control. And there's a big difference between those two because angular orientation control implies position control. As you all know, there are 3 control loops that essentially are involved whenever you're running a motor: the torque control loop, which is inside the velocity control loop, which is inside the position control loop. Normally drives are run in the velocity control loop mode, and less frequently we run in the torque control loop when we're doing things like constant tension center wind on a big paper roll. But we rarely run in position control loop, except when we use the special software features from Yaskawa in products like the electronic line shaft, in spindle orient, in our indexing control for induction motors using the Yaskawa drives. So here we're talking about electronic line shaft, where we angularly control the motor shaft relative to this pulse train input that need not come from a master drive. It can come from any shaft. Now, how does this operate? We take an encoder input on the PGX3 to commutate the motor. We take a second encoder input on the second PGX3 card. We used to use a PGW2 card for this, which was a dual encoder input card. Some of you may remember that. That's been discontinued because we just didn't sell enough of them. And so we decided, oh, the heck with it, we'll use 2 PGX3s and increase the volume on that product. I think that might have been a short-sighted decision, because this takes up an extra. No, I take that back. The PGW2 card did take up 2 inputs, so scratch that statement. Okay, now, once you have your hardware set up in this fashion, and remember your best practices, good shielding, blah, 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 we then get into the parameterization of the software. You do not write code to let this software operate. It's parameters that are in the P section, which is normally empty in a standard drive. We fill the P section up when it comes to special firmware products. And it is just learning how to adjust the parameters to get the effect that you want. We have the ability to take the master encoder and put a ratio on it. So if it's coming in at 1,000 pulses per rev, we can divide by 2 or divide by 5 or whatever, and allow you some ratio control. I'm going to jump down to the P parameters. By the way, when we do this, there are often times where we have to manage the memory on the drive, so we'll drop other functions out of the drive. Don't be surprised by that. In the case of electronic line shaft, it's a pretty space-intensive software, so I'm sure we dropped some other things that have to do with fans and pumps that have no relevance to this software. And once you have flashed the firmware into the drive, those parameters are just gone. If you want to turn the drive back into a normal drive, well, you can reflash the original standard software back into the drive, no harm done. Understand this, these symbols next to every parameter tell you whether that parameter is relevant to the control mode that you're operating in. With regards to the electronic line shaft software, we will primarily be operating in closed loop vector control, and the parameters need to be relevant to CLV for you to be able to operate them in closed loop vector. Now, here are the new parameters. These are modified. They are parameters that you see normally in the drive. And remember, the F section of the parameters for us is option cards. And because we're using PGX3 cards, we have some F parameters that have been modified to the function of this particular firmware product. And I don't need to go through these in detail, but here, for example, you can set your pulses per revolution on the incoming pulse train. and the direction, et cetera, et cetera. Now, there's the second pulse train. And again, the similar. Now, in P101, the first special parameter associated with this firmware product, you now can select the various modes of operation from disabled to the electronic line shaft function, which is 4. The 1, 2, and 3 are velocity modes, and we've used those sometimes, but the main point of this software is electronic line shaft. In other words, electronic line shaft is basically, it refers to a shaft that is not chained or belted to a master shaft, but is electronically chained or belted to the master shaft. Therefore, positional control. When you're chained to the master shaft, you have no choice. The electronic line shaft tries to achieve that with minimum deflection, because obviously the two shafts are not physically tied together. So if there are severe load differences between the shafts, the chain would normally take that up until the point where the chain breaks. In terms of electronic line shaft, you have to be a little bit savvy in applying this, because you may get some deflection that will correct. But that's the concept of the product. Here you can set your ratios between the master pulse train and what you want the slave motor to do. You're all familiar with the concept of numerator and denominator and fractions. There is always a situation where if you have one number divided by another number that doesn't come out to a discrete number of decimal places, that you have remainder error. And we have a relatively primitive way when you compare this to motion control software, but we have a way of handling that. Now, I think you get the general idea of what this is about. Electronic line shaft, by the way, we have the ability to advance and retard the motor through an input that allows you to select timing on those of you that have tuned up an engine. You can advance and retard the point where the spark ignites in the cylinder relative to top dead center. Typically, you want to ignite the spark slightly before top dead center on a internal combustion motor, so that the explosion takes place as you're going through top dead center, and that timing is critical to the power output of the engine. Similar here, we can advance and retard the position of the slave shaft to following the master shaft. Now, this is not an in-depth class on how to do this. This is a class to introduce you to the concept, to be aware of the fact that the product exists, and how to access some documents, which I will put up on our team site, in order to learn how to do this. If you read the manual on this, you really won't need a lot of extra help to set this up. It's pretty straightforward manual. It's well documented. If you need some specific technical assistance in your first startup of electronic line shaft, we at Western Automation, Danny Peters from the applications group, we are available to help you. If you need specific on-site startup and you don't want to deal with it yourself, then depending on the situation, you may be able to armbar one of us to coming out to doing it. But typically, I would account for a technician to come out, and the local authorized service provider has technicians that are very familiar in electronic line shaft. And on a commercial sense, typically you will be able to hire these people for, I think, about $175 an hour, minimum 4 hours plus travel. So you may want to account for that in your startup during your quotation. I don't think it'll take 4 hours, but the minimum charge is 4 hours. So there you have it. Now, do we have any limitations on applying this? And power levels, you can apply it to any A1000 GA800 drive, all the way on up to the 1200 amp A1000. Can we have a mismatch between the master and the slave? Absolutely. It doesn't really matter. All we're interested in is that pulse train. What are some of the things that we need to consider in applying this software before we quote it and get in trouble? Well, we certainly want the customer to define in writing what the requirement of the application is. And that means how accurately we have to match the slave shaft to the master pulse train. That will be an overall accuracy number, usually in percentage of the master shaft maximum speed. So if the master shaft maximum speed is 1,000 to 1 and we're running the slave motor in a 1 to 2 ratio, therefore the maximum speed of the slave motor is going to be 2,000 to 1. We want our 2,000, then we want the master shaft accuracy to be defined in terms of a percentage of the maximum speed. We also want to understand what the maximum allowable deflection is during severe load differences and the critical damping time that we have to correct that to bring it back within the speed accuracy tolerance. So you have your speed accuracy tolerance and percentage of maximum speed. You have your maximum deflection allowed, which may be much more than the accuracy spec, or may not be any more than the accuracy spec. That depends on the actual application itself. And if we are allowed to deviate beyond the accuracy specification for a limited amount of time, we want to define the critical damping time that we have to get back to within specification. That's typically what you want to find out from the customer, and you get it in writing, because you really, in any of these applications, you don't want to be held there on a variable or undefined specification. You want to be able to go in, prove that you've done, what you've been told to do, and then you can exit out. If there still is a problem and you've proven that you're meeting the original agreement, well, at that point, you can help the customer for an extra charge or not, that's your choice, but at least you're going to get paid for the original purchase order. Now, the other thing about electronic line shaft is you really need to get a handle on the inertias involved on your loads. If you have an extreme inertia mismatch between what you're trying to follow and the follower, God darn it, this thing's blinking at me again, hang on. I don't know why it's blinking at me, but now it's not blinking at me. Okay, sorry, I thought there was another person trying to get in. The inertia mismatch is very important. And when you have a large inertia mismatch between the master and the slave, I'm going to say at this point, because this is a relatively low-level tech class on this, you need to talk to us, and we can help you with this. Now, I don't mean to insult some of you out there who have vastly more experience than I do in motion control applications and fully understand inertia mismatches in terms of servos. Same principles apply here. The only difference is with servo reaction times, we're talking about microseconds. Our control loops on this drive are 5 milliseconds, 3 milliseconds. So this is a much slower reacting motion control product than servo products that you may be used to. And the motor itself is a big dumb mule compared to permanent magnet servo motors with much higher power density and much lower rotor inertias. So when you combine the fact that you've got this trim athletic permanent magnet servo motor versus this big dumb mule of an AC induction motor, and you've got a servo amplifier that's closing the torque loop, let alone the velocity and position loops, in microseconds, and we're closing loops in terms of milliseconds, we have a lower dynamic response product in this, the electronic line shaft, in our motion control software, in our spindle orient software, anything where we're doing position loop control. Frankly, anything where we're doing velocity and torque loop control as well. We're controlling a big dumb mule, so we don't really need all this super fast and frankly expensive product. We don't need a servo amplifier here. We're doing this with a standard variable frequency drive, some firmware, and a couple of option cards. That's the real value to this. It's poor man's servo. It's induction servo. Call it what you will. Just understand its limitations. Okay, I'm going to move on now from electronic line shaft because again, this is a class to make you aware and give you sort of a general background on these things so that you can go out now and apply these products. The voltage PID software I spoke to earlier, this is an open loop software where we can actually just decouple the voltage control from the frequency control and allow the drive to become a power supply. It applies to all of the A1000 products. It has not been migrated to the GA800 as of yet. And this is how you set it up. Now, in doing so, this three-phase load need not be an induction motor. As I said, we've done it with medical power supplies. Note this. If this load is resistive and not inductive, the drive isn't going to like it very much. The more resistive it is, the more that it's going to look like a short circuit to the drive every time we fire a pulse on the drive. So we're going to put some filters in between this to keep the drive from tripping. We will also put filters in between the drive and the load to make the output of the drive less PWM and more sinusoidal, a la a sine wave filter, thus achieving both purposes. Here, we tap off the voltage reference that we feed back to the drive, and we perform a simple PID loop on this sensor input, this voltage transducer. And those of you that are familiar with PID control on the Yaskawa product, there's a gain and an integration time. And I don't need to go into PID theory here. We can certainly do that in another class, but that's the basic concept of this. This is a PID on a voltage sensor, very similar to PID on a pressure sensor or PID on a flow meter. The important thing to understand about this product is that you're dealing with a non-motorized load in many cases, and therefore you need to spec the correct filter. Now, there's something else that you need to understand about power supplies. And in the power supply world, we talk about the distortion of the waveform here at the load. And typically, we have to be concerned about the distortion of the waveform during load changes. The more severe the load change, the more dynamic the load, the more we have to be concerned about it. I'm going to use this medical power supply application because we used to sell a lot of product into this field. We don't so much anymore, and it is primarily because of the harmonic distortion issue. Remember, this old drive here is updating in milliseconds. The PID loop is updating in milliseconds. If we have a severe load change here, one, we may not be able to react to it as fast as the customer likes. And two, we may not have the energy reserve in the DC bus capacitors to instantaneously supply that through the filter, which also has a delay effect, to the load. And this is one of the reasons why we eventually got phased out of the power supply market for medical devices. In the early days, they just basically lived with that distortion. When an MRI machine or a CAT, which is, I think, computer aided tomography or something like that, these machines, they turn on and they have a step change in load. And they want the voltage waveform to be perfect during that step change. Now, that's frankly not possible, but they could live with the distortion and the lag of reaction time in this setup in the early days, where when they turned on the MRI machine, the sine wave of voltage here didn't look like a sine wave for a period of a couple of seconds until we could react. We flat topped the sine wave because we didn't have enough capacitance in the drive to immediately supply power. Therefore, we drained those capacitors out and we had to fill through the power line, increasing our reaction time and increasing the flat topping of the sine wave that went to the load. And we had a lot of distortion, which meant that the voltage waveform didn't look like a sine wave. Obviously, if you flat top a sine wave, it's got distortion. What eventually pushed us out of this market is the fact that power supplies with much faster reaction times and with much higher reserves of instantaneous power became less expensive and began to compete with the lower performance of this particular product. And by the way, that's what we originally developed this for. A lot of our special softwares were developed for specific applications and then generalized. I still use the voltage PID software. It's very effective for controlling welders. We have several customers that still use voltage PID for their welding control. And the instantaneous reaction time to load that is required in the medical business isn't required in welding. So this drive with the PID voltage software still has application today. This software, spindle orient control, this basically allows you, based on a digital input, usually from a prox, to orient the motor shaft by a defined number of degrees of displacement from the initial proximity sensor. We allow you to do it in a direct drive situation, and we allow you to do it in a drivetrain situation. This was originally developed for vertical mills in the CNC world. where you need to orient the shaft for tool change. Product works very well. It is available only on the A1000 because it requires closed loop control. And in the case of the direct drive, we can use the motor encoder. In the case of a belted drive, if you want it to be extremely accurate, you will use a second encoder input, very similar to electronic line shaft hardware setup. But if you want it to be less accurate, you will use a prox sensor as your input and only require one PGX3 card. Now, these are the three major modes of operation. Bottom line is this shaft gets oriented X degrees of displacement from your initial proximity sensor, or frankly, digital input. We don't care if it's a proximity sensor or not. It's just a digital input to us. And it comes in on the S1 terminals of the drive, which are our digital inputs. Again, we have special parameters for this. Oh, by the way, here we documented in these manuals what the deleted functions are. We took all this stuff out in order to make room for the particular product we're talking about. And here, again, we're modifying the F parameters to function in the specific software, and we're adding P parameters. These are the additional parameters we add. Okay? That's basically how all of our manuals are set up. I'm going to touch on this one. Note, this was not in the price book. This one's kind of near and dear to my heart because we developed this back at EMS in one of the Yaskawa private labelers during the 90s. A much primitive version of this. Since then, Yaskawa has really brought this up to speed. Again, this is induction servo. Dynamic response is limited compared to what you're going to get in a true permanent magnet motor servo. So let's get through all the boilerplate, and I'm looking for how we set it up. Hang on a second. Okay, we didn't have a diagram setting it up. Okay, these are our P parameters for setting up the motion control software. And this basically allows you to do indexed position moves. Here are your positions that you can predefine, and via digital inputs, you can tell the drive to move to them. And in this kind of software, I noticed that we put the P parameters, which are the additional parameters, ahead of the modified parameters in this manual. So he's not following format. Oh well. One of the things you need to understand about the motion control software is, well, whether your move is going to be absolute or relative. And again, those of you in the motion control world really understand what I'm talking about. But an absolute move is a move relative to a defined point. And that point doesn't change. Therefore, everything's measured from that point. When we make a relative move, we're making a move relative to where we are now. So if I put the number 100,000, so 100,000 pulses of the encoder. And then I put that into one of the position registers in the P parameters, and then I say go there. If it's absolute, I'm going to go to a position that is 100,000 pulses from the absolute start position. And whatever direction I have to go to get there, I'm going to go there. I'm going to move in that direction. If it's a relative move, then I've got to define which direction I want to go, and then I'm going to move 100,000 pulses from where I'm at in that direction. I hope that concept is clear. Again, we're not talking about extreme detail here, because when you want to actually use this and when you've applied it, we are perfectly willing to hold an online session with you to do specific training on how to set it up before you go to the field. Again, circumstance dependent and availability. We can help you with the startup. In many cases these days, I'm doing the startups remotely via some sort of web interface. And then you have the option of having a field presence by someone from Yaskawa Western Automation, or a paid presence from one of the authorized service providers. You know, those are your options. But the class today is mainly to introduce you to the concept of this and hopefully give you enough confidence that you can generate an application and a customer and a purchase order so that we can go out and do the aforementioned levels of support. With that said, this is a very complicated software. More than willing to answer questions if you have questions on this software before you go out to apply it. And the method that I would recommend that you send those questions into me is via the team chat so that everybody can see them. Certainly, if you want to send me an email, I'll respond to it, but I would much prefer that you send your application questions in via the team chat. And then do me a favor and text me and say, hey, dummy, go to the team chat, because I don't monitor it hourly. I typically check it every night. So if it's an urgent situation, do that, and it allows me to have that conversation in light of the entire team. Now, if you are worried about your specific customer and you have some sort of secrecy involved with your relationship there, then by all means, just send me an email and I will honor your discretion. So that is the sum total of probably the 4 most important application softwares that we have available as products. And I'm of the opinion that Yaskawa will move more and more towards their philosophy of software is free and allow you to download these and flash the drives via the Drive Wizard industrial software. And this, of course, we're going to charge you for the added PGX3 cards, etc., that are necessary to complete the hardware setup. But I think that's a good philosophy from us. I think that our policy of not charging for software that's who we are. We need to stick to that identity. There is value in these products, though, as you can see. And to the extent that they make our drive better than the next person's drive is all the more reason for you as a distributor and for your customers to standardize on Yaskawa, because we have these options when you need them. With that said, we're coming to the end of our time. Are there any questions that you have? I will say that I will probably hold a second session on some of the other special software products, because we don't do a good job of letting you know that we have these things. Again, you know, we're kind of marketing morons at Yaskawa. We develop a lot of really good stuff, and then we don't tell anybody about it. So one of the purposes of this class is to get this information out there to you. So expect another class, whether it's next week or not, I'm not sure, but we have probably another dozen products in the special software arena. And I'm going to close with this statement, because some of the special software stuff that we developed, say back in the 90s, we don't need anymore. And we can do them with the current drives in standard mode. So I'll let you know what products like that there are. And for example, some of the more sophisticated, well, they were sophisticated back in the day, commercial laundry applications that required special software back in the days of the G5 and the F7 model lines they don't require that anymore in the GA800, because the GA800 has that capability inherent. And last but not least, remember DriveWorks EZ. We had several sessions on the DriveWorks EZ class back in the August timeframe, I should say, when my friend Craig Swift was helping me. And that product is a product that allows you to create all manner of custom, one-off special firmware applications for the Yaskawa product line. So those applications where we have enough market for it, we come out with a product. If you've got 1 or 2 or 5 applications for a specific function that you don't want to have to buy a motion controller or a PLC to accomplish, then we use DriveWorks EZ. With that, I hope you've enjoyed today's class, and it's 8 o'clock, time to go to work. Thank you very much.